Okay, last time we were talking about memory management. We talked about why it is important to have a memory abstraction for the operating system, for the computer to have. Because if you don't have the memory abstraction, then memory protection, relocation, having more than one program in the same memory is not possible. So we talked about a few methods of having more than one program on the memory. And if you have more than one program on the memory, then memory management, allocation of memory for the programs becomes a problem, and that's what we were looking at. We said that when the memory is assigned dynamically by the operating system must manage it. And there are two methods of managing keeping track of the memory usage. One is the bitmaps, the other one is the linked list or the free list. We talked a little bit about this one last time. For the bitmap based memory management, we say that we divide the memory into allocation units, small allocation units, let's say a few kilobytes, maybe 3 kilobytes or 4 kilobytes, I don't know. These are 4 kilobytes memory segments, and each segment, to mark each segment, in order to keep the data about the segment, if it is used or not, we use a bitmap table. Okay, each bit here indicates that this one indicates that this segment is occupied or not. This one is used for this one. It goes like that. And if the bit is here is 1, then this part is used by some process. If it is 0, then it is not used by some process. So if you have a new process being loaded to the memory, and if the new process needs, let's say, 10 kilobytes of data, 10 kilobytes of memory space, then we would find the suitable position where this much of data is available for the memory, and we would get those. So we don't look at these ones, we check these zeros. So this is how memory management with bitmaps works. And since these are indicated only by single bits, it's very efficient. It is very efficient because for each 4 case, we use either a 1 or 0. So it is very efficient. Very efficient. In terms of efficiency, memory efficiency is no problem. But the problem here is that if we need to find the suitable location for a new process, then I have to search all of these holes. Okay, I have to search all of these holes. There is no easy way to find them, so I have to make a linear. Linear search. Okay. Yeni gelen arkadaşlar şu boş tarafa otursunlar. Okay, so that's the problem. Bitmaps memory is divided into allocation units, and size of allocation unit is a design issue. If it is large, what is the problem with it is being large? If it is large, then some of it might be wasted, and if it is small, then my bitmap by bitmap table would be very large. So because that would be many allocation units. So that would be the problems, okay? And searching for K allocation units is expensive because I have to check this bitmap to find the, okay, is this good enough for me, or is this good enough, or is this good enough? I have to check the whole bitmap table. These are the disadvantages of using the bitmaps. Another possibility of memory management is using the linked lists. Okay, I would keep a node for each occupied and available memory location, and I would say that, okay, starting from 0, 5 allocation units is occupied by a process. Then, okay, it is this one. Let me erase this. Because I'm going to draw this. Okay, this one says that, okay, starting from 0, 5 allocation units, 1, 2, 3, 4, 5 is occupied by a process. Then starting from address 5, that is here, okay, for 3, these 3 consecutive allocation units are available. It's a whole. Then I have a process here from 8, okay, from address 8, I have 6 allocation units taken by a process. Then another process takes this space. Then I have a whole here, starting at 18. And then it was like that, okay? So, what is the advantage of it, of this compared to the bitmap representation? It is easy to, it is when I have this type of representation, I don't need to keep a fixed size table, okay? Fixed size table. At the beginning, I have the largest memory available for all the programs, so I have only a single node or 2 nodes, okay? One for the operating system, maybe one for the whole, because the whole thing is available. So when the things start getting more and more busier, I will have more nodes. But going over these nodes is not a very difficult thing. I can do it. It is expensive. Still, it is expensive, but I can do it with a simple algorithm, and that's called the memory management with linked list. So it has both advantages and disadvantages. If it has so many holes and so many occupied nodes, this becomes a problem, because it will have so many nodes in the memory, and having so many, I mean, for each bit, if I have a node, that would be expensive, right? For each bit, if I have a node, then that would be very expensive. But if I don't have so many nodes, that would be cheaper to keep in the memory, and also it would be easy to walk over or traverse these linked lists. Okay, so we have a few examples here about how to merge neighbor blocks in the memory. Let's say I have a linked list. It says that process A takes this part, process B takes this part, and I am releasing this memory. Okay, when I release that memory, my memory becomes like that. Okay, but if I release this part, my memory becomes like this, because this is already available, and I release this memory and I make this a big chunk, similar to this one or similar to this one. So this is a 4 neighboring combination for the termination of process X. Process X terminates, I am releasing its memory, and I can do this kind of termination job. I can do this with both linked list type of memory management, and I can do this with bitmap memory management. Okay. So as I said, both have positives and negatives. So when we need new memory, if I am loading a new process to the memory, I need to find some place for my process in the memory. So what do? I need to scan, either I need to, okay, go over these ones and zeros one by one, or I need to go over these linked lists one by one and find some place. But there might be more than one place where my new process can live. So we need to come up with some algorithms to decide which place should I choose for my process to live. So these are 5 example memory management algorithms, and we are going to look at them one by one if there are no questions. Any questions so far? So don't forget what we are doing here. We had a few very simple memory management techniques that we talked about, like the swapping or the base and limit registers. For these to work, the operating system needs to decide where the program is going to live. Okay, so that's what we are doing, and this is how we are going to find the suitable location for our process. First fit. Let's look at the first fit. Traverse the list until a large enough block is found. If you are doing this ones and zeros bitmap type of representation, you would look for these consecutive zeros. If they are good enough, okay, then I would pick that location. That's called first fit. Okay, or if I have the linked list, I would traverse the linked list, and if I find a large enough block, then I would say that this is my spot. So allocate as much of it as needed. Traverse the list until a large enough block is found. I mean, if I say if I need 4Ks, and if I need 4Ks, and this place has 12K, right? This has 4K plus 4K plus 4K. This has 12Ks of place. Then I would allocate this place, saying that okay, I will turn this 0 into a 1, and now it will become 1 0 0, right? It will become 1 0 0. So this is first fit. You find the first large enough place and allocate as much as I need, and mark it that way, and continue. Okay, and return the rest to the free list. Okay, and when you are freeing the memory, must merge adjacent blocks that we already know, either with the linked list or the bitmaps. Okay, and if you are using the linked list, obvious solution is to order the linked list by address. Okay, so how do I order? I mean, this is already, the bitmaps are already addressed. Are already sorted by the address. Okay, because I know this is the beginning, then this is the next one, then this is the next one, and this is the next one. But if I am using the linked list, I can do the ordering using maybe by the available memory size, by the process ID, I don't know. But it says that if you are using the first fit, order the linked list by address. Order the linked list by the address. So this has the smallest address, then the next, it goes like that. So I am scanning the linked list by its address. Okay, this is called first fit. Any questions? A slight variation for the first fit. When I start searching for a new space again, instead of starting from the beginning of the linked list, okay, I should start from where I left off last time. Okay, I should start from I left off from last time. Okay, so don't start from this node. Okay, if last time if last time I allocated this space, then next time start searching from this position, not from the beginning, but from this position. That way, you won't have to allocate the memory from the beginning all the time. Okay. Otherwise, you would allocate the memory from the beginning all the time. Beginning of the memory would become fragmented. The other parts are more empty. So the next bit does this variation. So that's the only difference between the first bit and the next bit. Some people think that first fit wastes some memory. It wastes some memory because remember I needed 4K of memory. There is 12K available here. So don't use this much of memory. Okay, don't use this much of memory because maybe there would be some other better positions where 4K is available. So that algorithm is called best fit. Best fit. Not first fit, but the best fit. So the first fit seems wasteful. There may be an exact match further down the list. Remember, I was looking for a 4K of memory. When I saw the first 12Ks of memory for the first fit, this was good enough. So I allocated it. And I said that, okay, I will take that one. 4Ks will be used and 8Ks will be available. So I divided it into two. They say that don't do this. Scan all the linked list or all the bitmap and find the best available position. If I need 4K and if you find a space for 4K, available space for 4K, then that's your position. Okay, that's the best fit. Find the free block that's the closest in size to the request. If I don't have any available space of the size 4Ks, maybe 5K is okay because that's the closest I can do. Okay, so that's the closest I can do. So obviously the structure again. Maybe I should order the linked list by size. Why do I order the linked list by size in this case? Instead of by address, you say that order the linked list by size. Somebody said something?
Size'a göre.
So that's the question. Why do I sort the linked list by size? What is the advantage?
It will be quicker to find the suitable place.
It will be quicker. I mean, what is the
searching from beginning of my size?
What is the okay? What is the search complexity for this first fit? If I do it by address, if I sort by linked list by the address of the available memory location, it would be ON, right? And if I order the linked list by size, then log n. It's a linked list. If it's a linked list, then you have to search it, right? You can't do it by dividing into two, then the first part or the second part. Again, it is ON. But these are theoretical numbers. It would be very easy to implement if I order the linked list by size. Okay, implementation is continue searching until you find but on the average, okay, if I sort by linked list by size, on the average, I need to look at the half of the available locations, right? If I order it by the size, on the average, I need to look at the half of the available locations. But if I order them by the address, then I need to check all of them. So on the average, I will look at all n of them if I don't do it by size. Okay. So if I do it by size, then on the average I need to look at the half of the available applications. If I do it by the address, as I did for the first fit, I need to look at all of the available holes because I don't know which one is the best. It could be the last one. But if I order my linked list by size, then it makes the merging less efficient. Why? Merging was, if I order my linked list, by address, merging is very efficient because I know that if I am terminating this process, I know the neighbors. Okay, I can merge these two. If I do it by the address. But if I order them by the size, merging becomes less efficient. Why?
Addresses are too.
Hocam memorinin boşuna bölünmesini engellemiş olmaz mı?
We are talking about merging.
Hayır hani şey yaptığımız zaman hani size'a göre ilk bulduğu yeri girerse, size'a göre girerse istediği alanı alıyor.
Yes.
Ama ilk bulduğu yere girerse bu sefer daha büyük bir yer olup boşuna bölmüş olacak.
So why merging is less efficient then? We are talking about fragmentation maybe. We are talking about merging. It says that if you order them by the size of the linked list, it makes the merging less efficient.
Birbirine yakın adreslerin alınması daha zor bir ihtimal bu şekilde yaparsın.
Birisi başta birisi sonda olabilir.
Yes, when you are releasing some memory, when you are terminating your process, you don't know your neighbors in the memory because you sorted your available memory locations by the size. So your neighbors are the similar sized neighbors. They are not your neighbors in the address space of the memory. They are ordered by the address memory. So that's why makes merging less efficient. When you are merging it, merging is not an O1 operation anymore. All of these operations are all O1. Okay, these are all one. But if you are using best fit, when you are merging, you need to find your neighbors where they are in the linked list by searching the whole linked list. So makes merging less efficient. Okay. So and people looked at them, first fit and best fit. They found that okay, the idea with the best fit was that when you are doing the first fit, you are using more than you are wasting some large enough